So let's start with our new presentation. So I have like two screens. Here like is the screen with the camera, but it doesn't have like the presentation, and here's like the screen with presentation. So if I'm not looking to you, it's just because like I'm looking to the presentation. So let's start. Today I'm gonna talk about challenges that face the autonomous vehicles in general and in maritime environment specifically. And this is like our table of contents. We will start with introduction, the kind of sensors that we are using in maritime environment. Uh, like maritime environment is like a word meaning that the autonomous vehicles or anything that operates in rivers or oceans, sea, any time like this, anything like this. So then we will go to the challenges that these vehicles face in the maritime environment, and then like some of the proposed solution to overcome this, how we can evaluate at the end our method, industrial or even like for academia. And then like I will go with you to a quick example on Collab. We'll just load like a point cloud and we'll see like how we can deal with it. We'll just like do something called transact and I will show you like how we can do this. Just like a quick example, like to maybe like get your hands dirty with some coding stuff and how you can deal with point cloud. So let's start our journey for today. So introduction. Just a moment, let me close my Telegram. So for non-disturbance. So introduction. Any autonomous vehicles needs sensor to perceive the surrounding, and the sensors are sensitive to the surrounding environment. So like autonomous vehicles are like human. We need like our five senses to perceive the surrounding. We need like our hands to touch stuff and feel it. We need our eyes to visually perceive like what is around us. We need like our ears to hear what is around us. All of these sensors help us like, or all of the senses help us in discovering what is around us and avoid maybe like if there's an obstacle in our way, if there is something that is a threat to us, then we can avoid this easily. And it helps us in a lot of stuff. So for autonomous vehicles, the sensors are like our senses. It help it like avoiding obstacles and go around the environment like with ease and do like other stuffs. But for example, the sensors that are on a drone and sensors are on self-driving cars and or USV, they can be the same, but the environment is different. So like, so you will face in each like different type of vehicles that operate in a different environment, different challenges. So for example, for the drone, you know, like that the drone can move in X, Y, and also like it have like a Z movement, and also it can rotate around like the three axes. So like the drone have like free of motion in a lot of directions. For the car, it have only like it can move only in X, Y direction, but it can't like fly, for example. It can't move on the Z direction. And for the USV, it also like can move in XY direction, but it can't fly as well. But what is different between the car and the USV, for example, that the car doesn't fluctuate like this. It doesn't have like a roll pitch here, but the USV can have like a roll pitch here. So that's also one different thing between like the ground vehicles and the aerial vehicles. And this like for sure like add a complexity or a more challenge for the sensor. So for example, um, imagine that you have like a camera on a car and the camera on a boat. So what will happen that On a car, like you can see almost everything stable. Maybe like only when you have like on when you step on a pump, a speed bump, then maybe like the image like start to fluctuate. But other than this, most of the time it's stable. But in the like maritime environment, you will see it like fluctuating like this most of the time because of like the waves and this kind of stuff. So this is like this added challenge to the data that you bring from the boat, for example, and so on for all kind of environments. You will see like some differences, and today like we will talk like about some of them. So sensors used in maritime environment, most of the time, like you will see that boats use like mostly three sensors. For example, like they will use sonar and maybe ultrasonic and like for the like above the surface of water radar. So like each type of sensor like they have like a different physical properties. So like for example, you can't use a lidar under the water. It's not like suited to this kind of environment. LiDAR is like using like the light properties. So like it can't move in water. It will have like a reflection and diffraction. So it's not suitable for this. So under the water, probably you will use ultrasonic sensors or sonar sensors. And above the water, as you can see, like most of the boats use like radar to detect like if some object is coming with speed and so on. So this is like mostly the kind of sensors you will see in a boat. Also, you can have like other kind of sensors. You can have like besides the radar, you can have like a lidar. You can have a GPS. You can have an IMU. You can have a camera, and so on. So what is lidar? As we said, like lidar is some laser sensor that fires some lasers, and it can detect like where is an object is at what distance and so on. And the lidar like bring you like kind of a point cloud surrounding by you. So this point cloud is just like a cloud of points that have like a distance information for all the objects that are surrounding you. And the GPS, for sure, like all of us know what the GPS do. It just give you like your location, and the IMU is a sensor that can tell you what is your fluctuation right now, what is your speed, what is your acceleration, and all of this stuff. And camera for sure, like we know what camera do. And the radar is like just kind of a sensor that like it's kind of like can give you like what objects are surrounding you and how like they are moving in what direction, what is the speed of it. The difference between lidar and radar, they have like different physical properties. That's first thing. So the lidar is light detection. The radar is radio. Like they are using like micro some kind of microwaves. But for the lidar, it's light waves. So like there is a difference between them. The lidar can operate to up to 150 meter, but the radar can operate in some cases up to 5 kilometers. So like our radar here like can operate up to 5 kilometers. So what challenge do we face? So here, like for unmanned ground vehicles, as we can see, uh, like for example, like here's our car, and it's just like this is the point cloud from our car. And as we can see, like the point cloud here, we can see the point cloud in general is called, we call like the point cloud as a sparse, not like image. However, the point cloud for unmanned ground vehicle is more dense than the point clouds that you will see from a maritime vehicle or USV, unmanned surface vehicle. So, like for example, like the point clouds that you will receive from a car, it will be denser than a point clouds that you will receive from a boat. Why is this? Because like the point cloud or the lidar uh, laser beams hit the ground and return back. and it hit like everything around you. But in the water, most of the rays, when it hits the water, it doesn't reflect back. So that's like because the nature of water. Some of them return back, but most of them, like most of the time, it will not return back. So like that's why like we'll see that it's more sparse. Also, another thing that you'll find here in the autonomous vehicles or the ground vehicles, you will find that the the plane or the ground here is horizontal. Most of the time it's horizontal. It doesn't fluctuate like this. It's just horizontal as you are moving. Because like the car is stable on the ground. It's all the time it's have like a contact with the ground with its wheels. But the boat is fluctuating like this. It's not like horizontal most of the time. It's fluctuating. That's make like the point cloud fluctuating with it, and that's also a problem. So here, like it's not very obvious, but here, as you can see, like here's our USV. Some of risks go and return here, and some of them doesn't return. Uh, so it's more like sparse here, more than like the ground vehicles, and you will see like this fluctuation problem. Here, sure, like we can't see it because this is just an image, but if you have like a video or kind of stuff, you will see the point cloud is fluctuating like this. And we'll try to elaborate more about this. So here, as we can see, here we are just like our boat was, for example, here. This is our boat, and as you can see, like um, next to the boat, there's like these waves that our boat is generating, and it will look like this, and it will look like this. And as you can see, like most of the time, there is a sparse area, as you can see, and it can only detect if there's some ship or some boat around it. It will detect it, and but the ground in general, like, is not like the ground vehicles. Here's like a boat, so like most of the time you will not find some something. It's only like here you can see some stuff because like our boat is generating waves. So like you will see like some area around it, and that's it. And also I told you that there is a fluctuation problem. So this is like the horizontal surface. As you can see, like here's the boat is under this horizontal surface. This boat should be like on the horizontal surface if our data is coming correctly. So for example, imagine if this is a vehicle and this is a ground vehicle and it can detect like another vehicle. So this vehicle should be here. That's also a difference between surface vehicles and ground vehicles. So as we said, like as our boat fluctuating, like turning about its roll and pitch angles, so the point cloud will fluctuate with it. It will not be fixed. So, for example, like our boat is fluctuating in on this way, as you can see here, on this way. So the point cloud will represent it on the other way. If our boat is fluctuating on the other way, so our point cloud will be in the opposite way. So it will always like fluctuate with you. So this is the true problem, and this is you will not see on the ground for ground vehicles. Ground vehicles point cloud is not rotating like this. This is just like appear because of the nature of uh, like USV in maritime environment. This is a problem that's usually occur. And if you will do anything with USVs or boats in general, then you need to fix this problem before you proceed to anything you want to do. So also other challenges in like the maritime environment is the type of boat, and actually you need to take care of everything. So for example, if you are on a ground vehicle, it's okay. We can test, we can do some stuff. We can like take some like big space, and we can start like doing experiments and testing our uh, ground vehicle. But for boats, it's harder than like what we can do. Experiments on boats is dangerous to some how, and if you don't take care of, you can face like some problems. And I will show you like some of the problems that we faced before. So here, like this was a boat that we used before. This boat have like some kind of sensors, lidar and cameras and rudder and everything. It's a small boat. It can fit 2 to 3 peoples. However, one time we were conducting some experiments, and we give like the boat like maybe some extreme control signals. And what happened is that the boat flipped with us. So like that was a problem. You need to really care about what you are doing uh, while you are like using your USV, because like maybe wrong signals or any kind of like maybe like a days that have like a very high waves or a windy day, this can cause like a lot of problems. It's really unpredictable environment, and it can cause a lot of troubles. And for sure, like while we were experiment or we were doing like this experiment while we were on the boat with our laptops, so like our laptops drowned, we could lose our life. So you need really to care about what you are using while you are using boat. It's somehow also this applied to ground vehicles, autonomous vehicles, self-driving cars, anything. It's also applied to it. You need to care what you are doing there, but it's still more safe than doing it in maritime environment. So in maritime environment, it's really hard to like conduct this type of experiments while you have like this roll pitch you, and if there is a windy day, the weather also affect you, and it's unstable environment. So you really need to take care of what you are doing. Otherwise, you can like end up something like this. So some of the proposed solutions is will like see now. So one of the proposed solution is that for the data that is coming from the data that is coming from the sensors, like here, the lidar and the camera and everything, and to fix this fluctuating stuff, what you need to do is maybe like introduce the IMU, because like the IMU can feel like how you are fluctuating about the 3 axes. It can help you like uh, in this kind of stuff. Uh, so like the IMU tells you like how you like where is your boat are now with respect to the world, or how your boat is moving with respect to the 3 axes for each moment. So you can take this kind of information, you can mix it with the point cloud, and you can give like a correction. So like you can make your point cloud most of the time horizontal, like the ground vehicles. You can like transform this. And also not all only for point cloud. Your images is fluctuating most of the time. So like if your camera will feel this fluctuation. So like your image will be unstable. So also you can use the IMU to like stabilize your image too. And this is a very important step. So you remember this image? There was here like these boat rebels and a side view for this. This is like kind of a top view or isometric view for this scene. And if we look like to the side view, we'll see like that this ship is under the horizontal line. This is before the pre-processing or before using the IMU and the point cloud to do the correction. But hence, after we use IMU, as you can see that we could remove like these rebels, we could remove like this because like most of these rebels around your pod, most of the time they will be like above the horizontal line. So you can remove them, and actually after correcting the point cloud, you will see that this shape or any kind of object will be like above the horizontal line or in its correct place, like how we can see in for the ground vehicles, for the autonomous vehicles. And actually, this is a very critical and important step before using your data, because like using your data without like doing some kind of step or this pre-processing, it will be hard. You will all the objects around you will not be presented in its correct location. So you need to correct the location of each thing around you or all the objects around you. So like this is one of the proposed solution. And as you can see here, after doing this correction, sorry, as like no matter how is our boat tilt, so the IMU will find a way always to feel this tilt and it will correct it. So we have like our point cloud, it was like this, should be like this. But when we know that how our boat is tilt and we multiply this tilt correction multiplied by each point in the point cloud, then we can have like a correct point cloud, which will be always horizontal. And this is like a very important and critical step, which you should like take care of. So this is like how you can correct your point cloud, and also the same way you are doing here, you will do it to the camera. Uh, you will have like you will use the IMU, and you will correct the camera so it's stabilized, more stabilized. There is some algorithms that can be used without the IMU, but the IMU is like mostly it will be efficient if you have like a good IMU and you can use it. So also, do you remember like this boat that was small and it's flipped with us? This is also was one of the problem. So how we fixed this, we had like a new boat because like the other boat was really unsafe. It can also have like it can only have like 2 to 3 peoples, but a new boat, this was like a larger boat, equipped more probably than the other, and it can fit up to 10 people, and it's way more stable. So like even if we give it a wrong signal, it will be more safe than the other. However, any wrong signal for any kind of vehicle, even if it's ground vehicle, it can make it flip or it can make it like do like a very like dangerous behavior. So all the time you need to take care of this. However, uh, like a more safe vehicle is also always recommended. So this was a new boat, as you can see, and it have like some kind of submarine here. The submarine can go down and investigate like some pipelines and stuff like this. So, and this is like the sensor blocks that we talked about earlier, the GPS and the LiDAR and the radar and 3 cameras down there and IMU. So, and this was like our first launch for the new pod. Here we were testing it, how it's doing, and actually it was like more safe than the other pod. So also like after you finish, you can like after you correct your point cloud, you can start doing your clustering. You can cluster like each object. So like every like close points to each other, they are representing kind of object. So like for example, this is a ship, this is another boat, and so on and so forth. So you can start like clustering like your objects by distance or whatever you want. But before you do this, you need like for sure to do like the pre-processing so you can detect each object in its place. After this, you can like maybe giving like each object a bounded box. This bounded box will be like critical for you to know like the orientation of the other object around you, and to know like the dimension also of the other object around you. And later you can start track this object, for example, and know like more about like its uh, speed and all the other information that you need for safe tracking. So here, like it was some test. So I was trying to maybe track this kind of objects. Uh, so like I can here, like it was not the best, but I was trying to enhance it more, and now actually it's better than what you can see now. We can like track this kind of objects around us, a small boat or a big ship, and we can know like the dimension, the position of it, the velocity, and all of this kind of information that will make us like better have like a better navigation in our like world and avoid the obstacle safely. But if we don't know like the correct position of the surrounding objects, this is will be like so dangerous for sure. As you can see, like it can still track like this big ship and this small boat. But as you can see, like here, for example, this is like uh, not the best because like sometimes it can detect like near objects together. So for example, if there's two boats are near together to each other, it can detect it as one object. And doing this is bad for tracking. This is also like from the challenges that we face here. And here start to can see like some kind of buoy, like a small buoy, uh, small floating buoy. So it's also like we need to detect this in order to avoid it correctly. So this is like regarding the tracking. So after you done with your algorithm and pre-processing and all of your stuff, you need maybe to do the evaluation, especially for academia, because every like new algorithm or everything you do, like you need like to evaluate it before it's being published or before it's even being used. So what you will need to use is use like some kind of simulator because like or some kind of data that have like a ground truth because like the ground truth is the most important thing. So what is a ground truth? Ground truth is that, for example, like you have like this kind of simulator and you know where exactly is this boat and this boat and this place. So you know like the position of each object around you in each time frame. This is a very important stuff. So you can evaluate your algorithm. So like you know the ground truth, you have like this ground truth, and then you will apply your techniques and algorithms, and you will have like an output, and then you can compare this output with the ground truth. This is a very important step. So for example, like we know like the ground truth position of this object or this ship and the ground truth position for this ship. And then like our pipeline after the pre-processing and after tracking, clustering and tracking and all of this, we can get like the position too. We can compare this position. So like the more close our output position to the ground truth, uh, like the more correct we are. So like this is an essential step that can validate like how good is your method or how good is your proposed solution. So as you can see here, uh, here we're using like these two boats and one of the boys as a ground truth. So what we can see here is that uh, before we are doing or before we integrate the IMU with the point cloud and fix this fluctuation problem, as we can see, like it as you can see, like it's just like looks like a sine wave. So the difference between the ground truth data and the output from our pipeline without integrating the IMU, it can reach up to 3 meters, as you can see, or 4 meters, for example, here. And this is a very wide range. So what is happening is that we have like a boat, and our boat like our pipeline is detecting that the boat is here while the ground truth of boat is here. So like this difference is about 4 meter or negative 4 meters. So like this is huge. So like the ground truth is here and our point cloud is doing like this because of the fluctuation of our boat. This is very bad actually. So after integrating the IMU, as we can see, like here we have like these three objects, the black boat, this is the black boat and the white boat and a kind of like a buoy. So for the black boat, the further also what we need to say also the further, the more like distance you will cover. So like as like the more further you are from our boat, then you will have like a large fluctuations. And this fluctuation also depends on like the waves. So like our boat is fluctuating and the other boat is fluctuating as well. So like it's a combined sine wave between the two boats. So as you can see, like it will look like somehow sine wave. Sometimes it's have like a big peak and sometimes smaller peak because like it's just like interference between two waves. And for the black boat, it was larger because like it's the furthest, and then the white boat and the buoy, as you can see. After doing the uh, correction, as you can see, how much like these fluctuations just reduced because like we introduced this IMU fluctuation. So now we are correcting our boat's position. So like it started to like be very small. It's only like about 0.3 meter, which is acceptable for now. Here like it was almost four up to 4 meters. Here's like almost 0.3 meters. And also like we can even enhance this more by the tracking. So like when we introduce also tracking, this like actually reduced to almost 0.1 or maybe less, like less than 10 centimeters in fluctuation. So this is like one of the important things to evaluate your model. And as we saw here, like how introducing the IMU can reduce this kind of errors. So here we finished. I want to give you like maybe a quick example. This example is how you can deal with a point cloud. So let's start together. So can you see my screen now? The collab screen.
Yes, we can see the
Great.
screen. We can see the graph.
Great. So here I will give you like maybe some quick example on how we can deal with point cloud. So it will not be like for maritime environment, it will be like a normal point cloud. For like just a simple point cloud, I will just like tell you like how you can deal like with some sort of some points, and I will give you like this um, like a notebook. You can use it. Actually, like this notebook is not mine. I found on the internet. I see it like as a good exercise, and maybe I just modified it somehow because like it didn't show like for any visualization. So I tried to make it with some visualization so you can use it later. So before we start, what I want to explain here is that there's something, some sort of algorithm called Ransack. The Ransack algorithm, maybe some of you like heard about it. So the Ransack, imagine that you have like some kind of points like this. So the Ransack is just trying to fit a plane or a line, and how it can fit this line. So like it just like try a lot of equations for lines or for planes, and it have like this threshold. So like it sees the distance between each point and the line, and the more points it have to this line or to this plane, then this is like a good candidate for a plane fitting. So this is like a very important algorithm, and it's used a lot for point cloud to detect planes or For imagine that you have like this ground vehicle or surface vehicle, and you need like to eliminate like the surface around you, or the ground around you, because like it's you don't need like the ground, you need only the obstacles. So you will find a lot in for autonomous vehicles. So you need like to fit a plane. So the Ransack algorithm is just will give like a lot of random planes, and the planes that will have like a point that is below the threshold that you will like define the most points, then this will be like the chosen plane for the Ransack. So let's start. Uh, Here we just like we are downloading like these two libraries. The Omnis 3D is a library that is dealing with the point cloud you can use with Python. And the Python code tree is just a kind of a library that we will use for visualization, and for sure NumPy. All of you like know like NumPy arrays and all of this stuff. We have like this .ply file. So like for point cloud, you can have like different type of like different type of extension. So like a point cloud can be a BCD file, it can be XLY file, and it can be .ply file. So like it have like a lot of extensions. So whatever your point cloud is, you can always like find a way to just load it. So our file here is .ply extension. So here we will load it and we will visualize it. So it's just kind of a kitchen. Uh, I will show you now. Just like take some time to load. I will also share this with you. So as you can see, like this is a point cloud, how it's look like. So it's just like a lot of points that is all together, that is forming like some object or some shape. And as you can see, like here is like a kitchen, which is formed by a lot of points that are together, and you can see it from all the sides, as you can see here. So what we are trying to do now, we want to like for this shape, we'll give it like all the points, and we will tell it like find a Ransack or a Ransack plane for it. So what is this Ransack plane is, it's just like it will try to make some random planes, and the most planes that have like the most points, it will be chosen as a plane. So like what can be like this planes that have the most point? It can be like the roof, for example, like the roof have a lot of points, and this is also like a flat plane. It can be like the side of the house, and also like inside the kitchen, there is a lot of planes here, for example, but I believe like that the side here and maybe the top will have like better chances. So we'll try and see. And as you can see here, like there's some lights. So we'll try like fit a Ransack and see like which plane it will be extracted here. So for our Anzac, like there is a threshold that we choose. So we are saying that we want like any point for this plane that have like a distance of 0.01 meter, for example, like which is 1 centimeter, to be included. Uh, so this is how we can do it. And the number of iterations is that we are saying that, like, for example, you can have like 1,000 iteration. You can try 1,000 time. And in this 1,000 time, you are trying a really random values to fit this plane. And the ones that have like the most layers in this threshold, you will use. It will be used and it will be fit, and we will take like the point clouds that belong to it. So let's try and see. So here, like we run this algorithm, and here we are visualizing only the inliers. And in the other one, we'll try to visualize the outlier. So we'll see here what will happen. So as you can see here, this is the inlier. It gets like probably the roof, because like it's a plane and it have like the most points here. And if we visualize like the outlier, just takes some time because like of the visualization. Like this notebook didn't have like this visualization, so like I tried to implement some stuff like to visualize it, as you can see. So here like is the outlier. So outlier is anything that wasn't fit into this plane. As you can see, it's like removed like this roof. But as you can see, like because the threshold was only 1 centimeter, so this lights stayed with the outlier. So what if we uh, increase this threshold to 15 centimeter? So it was 1 centimeter. Now we will like try to play with this threshold. We'll like make it bigger. So it will be now 15 centimeter and we will see. And also like one thing I want to say is that it's not all the time it will be the same. It can be close. So like if two run the same algorithm, maybe they have like a slightly change in the outputs, but still acceptable. So like most of the time, it's I use the algorithm for the unmanned ground vehicle or the unmanned service vehicles. It's only used for most of the time. It's used for like eliminating the ground around your vehicle. So just a little bit, just I don't know. It's but. Uh, feel like now it's not responding. I don't know why. Okay, let's try one more time. See, sometimes it's just like got like lag and it's need like to reset. However, like this is not playing on my PC. This is playing like on a cloud for Google. Let's just start it from the beginning again. And yeah, here. As you can see, like now it can take or can fit like a more wider plane, and it can also take the lights here, and the other one will be like without lights. So it's always like depend on like your parameters, your algorithms that you are using, and the parameters you are use with this algorithm and all of this stuff. As you can see here, it just like removed this light as well. So uh, we finished. I take like more 5 minutes. I promise you is 20 minutes today. However, like we have like some time, I believe, so you can start asking your question. Thank you for your listening, and we can start now.
All right, everybody, if you have questions, you can ask them in chat or you can raise your hand. To raise your hand, you go down to reactions. You'll see it in the menu. Click on reactions, and then you'll see a bar to raise your hand. Okay, we have a question from Ismail Adebola. Can you activate your microphone, Ismail?
Okay. Hello, can you hear me?
Yeah, we can
Yes.
hear you.
Yeah, thank you. Doctor. Thank you, Professor. Yeah, my question goes to USB. Can you hear me?
Yes, I can hear you.
Yeah, USB. That is a unmanned surface vehicle. Yeah. The question is this: as an automotive engineer, how can we design a safety USV in spite of fluctuation and opposition of some animals in maritime environment?
Okay, can you repeat your question one more time, please?
Okay, good. I say my question goes to USV, that is unmanned surface vehicle.
Okay.
Good. So, as an automotive engineer, rather, how can we design a safety USV in spite of fluctuation and opposition of some animals in maritime environment?
Okay. Uh, that's a great question. Usually we design for like the ground vehicles. Yeah, we take into consideration like if some kind of animals that is crossing the road or any stuff like this, and if it take like for example like a fox for example that is crossing the road, then the lidar probably will detect it and the car will stop. But for the unmanned service vehicles, like actually it's the same. So most of the time that like uh, we can see like the sea creatures or river creatures, they are under the level or surface of water. It can most probably it will be detected if they are above the surface, but under the surface you can use like kind of sonar or ultrasonic to detect this kind of creatures and try to avoid them. So this is how. So like yeah, that's also a challenge. Because like for ground vehicles, you can use like all the surface sensors and detect anything around you. But for the unmanned surface vehicles, you need like underwater sensors like the sonar, the stuff that we talked before, these kind of sensors to start detect like if there's any creature. So like if your environment that there is a lot of creature and you need to avoid them, then you probably will need like kind of a sonar that can detect this kind of creatures.
Thank you.
Welcome.
Okay, we are ready for more questions. So I have a question. How could a regular person apply this technology?
Uh, okay, so how can a regular person apply this? Probably you will need like to have like skills in some skills in some like tools, so and some programming language. So like mostly for robotics and this autonomous vehicles or automotive industry, you'll need like to have Python knowledge and C++ knowledge. It's critical and important, and most of robotics application will deal with these two languages. You will need to have like maybe some skills in CUDA and how to use the GPU, because like some algorithms it's really heavy and you need like to be more efficient when dealing with these like heavy algorithms and that like deal with like that have like a complex time, because like like robotics need to handle everything in real time. So like you can't, for example, apply a pipeline that can take 5 seconds to give you like a response. So like this is very dangerous, especially that autonomous vehicles is dealing with human lives. So I can't wait for 5 seconds or even 1 second. It just needs to be in milliseconds. So like if there is a boy, for example, is crossing the road, then I need to take care that there is a boy and I need to give like an output like in a no time. So this is also very important. Maybe you need like some applications that will handle this kind of middleware messages, like ROS, for example. robotics operating system. It can handle like your like stack or kind of algorithms that are dealing with each other or talking with each other in like in a fast manner. So this is also important. Maybe like you will use Linux. Maybe Linux as an operating system is more suitable for robotic stuff than Windows. What else? Maybe you need like to have like some Docker knowledge. It's better to have like Docker knowledge for any software engineer because like it's like facilitates the work within a team, and all of this stuff like can help you like in applying this kind of technology.
Okay, now we have a question from Samuel McNeil. Go ahead, Samuel.
Yes. Thank you, Doctor, and thank you, Mohamed, for this wonderful presentation. It's just very interesting. It's not my field, but I like the way you are doing it, and I'm enjoying it.
Thank you.
I bought a vehicle, Mercedes-Benz, a year ago. I was driving on our own road. My question is on the ground sensors. As I was driving, our roads are not straight roads. They had a bend, kind of. I was so shocked the vehicle, somehow it just went down the other side of the vehicle. I mean, everything went out of me, worried to say I'm making an accident here. And later on, the vehicle picked it normal, driving normal. What kind of sensor is that? Because from your explanation, looks like the ground vehicles, they don't have the fluctuation sensors. They are able just to, you say horizontal something there, right?
Yes, right.
Exactly. So I'm just wondering to say what kind of sensor, because my vehicle dropped one side and they said it was sensor. So I don't know what kind of sensor was that.
Okay, so let's revise this if I understand your question
Sure.
correctly. So here, like, this is the lidar. The lidar can detect like the like environment around you in a horizontal way. However, for example, like imagine that you have, as you are saying, like a roads that are not horizontal. So for our vehicle or our vehicle, it's still constant. It's still like have a contact with the ground. So for us, it's still a horizontal environment. So what the ladder is giving you about this fluctuation is because of the type or nature of the ground around you. It's not because of the nature of the environment itself. So, for example, like at one moment you will not see like the point cloud is fluctuating like this. However, it depends on like where is the car it is with respect to like the environment. So for example, like if our car like on a speed bump, so it can have like some feature like this. So it can like give you like some kind of false information. However, it's with respect to the car. And actually, like dealing with this kind of problems, yeah, we faced before. We faced this, and we managed to like to find some solutions. However, this is different from what is happening for the service vehicles. So, like for ground vehicles, it's a different challenge that what is for service vehicles. So, for example, like for service vehicle, it's this fluctuation is happening because of the waves. For the ground vehicles, these fluctuations is happening because of like the uneven terrain of the solid ground around you. So like it's different type of challenges. Hope like I could like elaborate this. And if you have other question, you can ask it.
Yeah, well, I thank you very much on that one. On the same day, it was my first day to drive the vehicle. Um, our roads, yes, they are, well, not that good. I mean, most of the roads, but this time, you know, these solid white line on the road. So
Yes.
as I was driving, I don't know, every time I went closer to the white lane, solid one, I could see the vehicle stopping. My worry was for the person behind me to say, what is going to happen? So as we were explaining, those things came in my mind in the sensors of what we are going through on the road. And sure, so I don't know if you have anything to say on the same.
So about the white lines, if I understand you correctly, that your
Yeah.
vehicle is telling you like maybe you should like stay on your lane or stuff like this. Uh, this is probably implemented in most of like a lot of cars nowadays, especially like electric vehicles. This is like not an autonomous solution. It's just like it's called an ADAS, just like assistant driver solution. Just like some small camera that is placed in the front or maybe like beside your mirror, and just like can detect like the lanes, the white lanes, and if it's just, for example, see you that you are getting near the line or getting out from your lane, it will just like try to assist you. It will just like give you like some noise or some kind of information on the screen that is saying like just turn right a little bit because like you are out, you're about to go outside your lane, just like trying to help you in making your driving more safe. And like you can also like for example, like you can have like also an ultrasound sensor that if some object came in front of you suddenly, it can assist you and it can make a breaks for you. So like all of these systems is just like assistant driving systems, and even like this kind of uh, rudder rudders in the back of the cars, it help you like in parking. So like all this like are just to help you in your driving and like to give like a more safety for the others around you.
Thank you. Thank you very
Welcome.
much. Sure.
Thank
I
you for those
appreciate
questions,
it.
Samuel.
Yes.
Ismail, do you still have a question that you want to ask?
Actually, I don't have. I don't.
Okay, Mohamed Ahmed, we have come to the end of the hour. What would I want to ask? What would you talk about next time when you come back?
Uh, Actually, like I don't know yet. Maybe I will try to make maybe like a more practical examples and something like what we did on collab today. I will try to make for them like some kind of like more visualization stuff and how they can use it. Maybe like we can start like together go step by step, so like they later can do whatever they want. But we need like to start with some Python, like some examples, some like small examples. So like maybe I'll try to make it more practical.
Like, how could you apply this to someone who is blind?
Uh, okay, so how we can apply this to someone is blind? That's really good question and and big question. So we can start by making like some small examples with just like how I did today. Maybe like a small file of point cloud or an image that is coming from this sensor, or maybe a small file also of sequence frames with IMU data with all of this stuff. And I will try maybe to like let them use it. So like there, for example, like there's something called Kitty dataset. You can start maybe using it, and this Kitty dataset we can use it with Python or with uh, C++. You can see it just like it have like sequence of images, and it have like a point cloud for this scene. It have IMU. So like maybe we can start diving in this. We can like see like how this data is looking like and how we can use it and what we need to achieve and how we can achieve it. Maybe you can like start talking about this more.
Okay. Okay, thank you very much. I don't see any more questions. And so I think that's the end of class. So everybody, thank you so much, Mohamed Ahmed, for your
Thank you.
presentation. Everybody now
Thank you.
you can unmute your microphones to say goodbye and thank you.
Goodbye. Thank you.
Goodbye. Thank you.
Goodbye. Thank you, Doctor. Goodbye.
Bye.
Thank you,
Good to see everybody
Tamara.
today.
Thank you.
Goodbye. Thank you.
Thank you.
Bye. Thank you.
Keep working on your assignments.
Thank
Team
you.
20
Thank you.
subject.
Thank
Thank
you.
you.
Thank
Goodbye.
you.
God bless you.
Bye.
Thank you. Bye.
It's a
Good.
God bless
Bye.
you.
God
Bye.
bless you.
Have a
Thank
great day
It's
and a great weekend.
nice.
Great day all.
Thank you. Bye.
Good.
Bye.
Good weekend,
Bye-bye.
everybody. Thank
Thank you.
you.
Bye.
Okay. Good night, everyone.
Thank you. Bye.
Thanks.
Bye.
Thank you. Bye.
Dr.
Bye-bye.
Lambert.
Thank you.
Bye-bye,
Bye.
everybody.
Zico.
Good